This video deals with pulleys and inclined planes. With pulley systems, you're going to want to ask yourself, how will the system move? Meaning, if I have an object on a pulley tied to another object, once I let everything go, where will it start to move? Then, with this, you're going to designate a coordinate system. Here, you can already see that my pictures show me that my string's going to act as a x direction. So here we have x going side to side and y going up and down. But as we look at the other side of our pulley, the x is going up and down and our y is going side to side. So what we're really looking at is for this entire string to be my x direction, and anything not in that direction is in the y direction, as we can see over here. So with this, it's going to be very important to draw a free body diagram, just like all problems. But what's going to help this situation is that all objects will have the same tension and the same acceleration. So, even if I have a tension, this t right here is the same as this t over here. And again, if I have an object that's accelerating, both objects will have the same acceleration. This problem is a very typical problem that you could see either on a multiple choice section or the free response section. This thing is called an Atwood machine. It was used to calculate what gravity is. Here I have two objects, one of mass m and another of mass 2m. So here we can see that the relationship between these masses is that one is twice the size as the other. For now, I'm going to label them as mass 1 and mass 2 so that I can make this situation a little bit more general for when you see a problem like this and the masses don't always have a relationship to each other. You then want to ask yourself, how will the system move? And make a guess. So I'm going to guess that my system will move in this direction. So I'm going to call this my positive direction. So anything in that direction will be positive, anything against that direction will be negative. So now that I have my system designated, I'm going to go back and draw free body diagrams for both of these objects. So here are my free body diagrams. I have tension and mass times gravity for both of them. And then I'm going to show that this mass times gravity is going to be positive because, again, it's in the direction that I said was going to be positive, and this tension over here is also going to be positive. Then I'm going to write the sum of the forces for each object. So for the first object, I have tension minus m1g is equal to mass 1 times acceleration. Again, it's really important that I make sure that my mass 1 over here is what I'm talking about in my object. The second one's mass 2 times gravity minus tension is equal to mass 2 times acceleration. Again, I know that these accelerations will be the same and these tensions will be the same. So I have two equations with two unknowns. This problem's only asking me to solve for acceleration. So in order to do that, I'm going to rewrite my first equation to solve for tension. Now I have an equation for tension is equal to m1a plus m1g. Now I can go to the second equation and plug that in for t. So that my equation looks like m2g minus, in parentheses, m1a plus m1g, close parentheses, is equal to m2a. Now, the whole point is to get acceleration by itself. So at this point, I can just algebra out so that I get acceleration by itself. Make sure that you distribute this negative here. So if I rewrite my equation, it looks like m2g minus m1a minus m1g is equal to m2a. Again, I want to get accelerations together and by themselves. So I move this to the other side. And now I can see acceleration is in both pieces, so I can actually factor out an acceleration. And this is all equal to m2g minus m1g. And finally, divide by m1 plus m2. You could have factored out a g. It would have been identical. Now, this equation is general for all Atwood machines when you have two objects. Because I didn't represent them as 2m or m, now I can actually go back and say that mass 2 was actually 2m, Mass 1 was just m. Mass 1 was just m. Mass 2 was 2m. So that cleans up to mg divided by 3m, or just g divided by 3. So this is, again, only true if I have a relationship between my masses. If it's not, then I do want to go back and just use the general equation for an Atwood machine. Now here I have a very similar object. I'm not going to answer the entire thing, but I'm going to show you how to set it up. Here we have on this first object, and we're going to call this mass 1, that we have a normal force up, we have a force of gravity down, and we have a tension to the right. On the second object, and we'll call this mass 2, we have a tension going up and then a mass 2 going down. Again, I'm going to decide what I think should be a positive direction. Again, the reason that I'm deciding, or how I decide what direction will be positive, is how I think the system will move. So I think it's going to move to the right, therefore I'm going to call to the right positive. So now, if the problem's only asking for acceleration and tension, I'm really not concerned with my normal force or my force of gravity on my first object, because I can see that that's not going to actually affect my acceleration. Especially if, in this example, we are talking about a frictionless system. So, I'm going to write the sum of the forces for both objects, which ends up being tension is equal to mass 1 times acceleration for the first object, and mass 2g, which is positive because, again, it's in the direction of what I said was positive, minus tension, again, because it's going opposite the direction that I said is positive, and all of this is equal to mass 2 times acceleration. Now, again, in these particular problems, my tension and my accelerations will be the same. So, 2 problems with 2 unknowns, I can just substitute and solve. So I replace tension with mass 1 times acceleration for my first equation. And then now I just have one unknown variable, which is my acceleration. So get it alone and by itself. Again, this is very similar to what we just saw on our Atwood machine. Ooh, I dropped a G here. And then the last piece. Again, you see that this is very similar, almost identical to our Atwood machine equation, except now we don't have that subtraction of my other mass. So if I know all my values, then at this point I can plug in my numbers. Again, you want to get comfortable with solving these in terms of equations before you put in your numbers, because again, on a free response, it's very likely that you're not going to have numbers. Now, if I wanted to go back and solve for tension, well, I already have an equation for tension. So I can go back to the first equation and say, well, mass 1 is still mass 1, but now acceleration equals to this entire mess that I solved for down at the bottom. And then we know all of these numbers, so I would just need to plug it in and solve for tension. Now, when I have an object that is sitting on an incline, I did something slightly different with it. Let's say I had a box. I know that my normal force will be perpendicular to that box. I know my force of gravity will be downwards always, regardless if it's on an incline. And let's say that this box is at rest, so I know that there has to be an upward force, most likely friction. So if this is true, I can see that most of my forces follow this coordinate system set in this direction, where x is slanted and y is perpendicular to my surface. So when this is true, the only force that is not like this is my force of gravity. So it's a lot easier for us to say, well, the only thing I need to break up into components would be this force of gravity. So I need to make a component of that force in the y direction, and I'm talking about my new y direction, and then a component in the x direction. Again, that's my new x direction. Now this angle in green is this angle here. Okay, and if you'd like me to prove it to you, just ask me in class and I'll go ahead and show you. So if I have an angle that's like this, then opposite of that angle will give me mg sine theta, so that becomes this piece down at the bottom. And adjacent to that angle becomes mg cosine theta. Again, once I break an object, or I'm sorry, a force into its components, I really don't need that force anymore. So, if I were to write the sum of the forces for this particular object, my y direction would be, the sum of the forces in the y, would be my normal force minus my mg cosine of theta, and if this object is at rest, then this is equal to 0. Now my forces in the x direction would be mg sine theta, and I can say that downwards is positive in this case. Again, I'm just deciding that. And friction is against that, and all of this is equal to 0. If this object was accelerating, the only one that would need to change would be this 0 down at the bottom. Instead of it being 0, it would be equal to mass times acceleration. This one would not change because it's not accelerating in the y direction, even if it was moving. So, when you have an object on an incline, make sure that you rotate your axis, break the weight, which is your mass times gravity, into its components, write equations of motion or equilibrium, which is our sum of the forces over here, and then solve for whatever we need to solve for. Again, for this problem, we have both pulley systems and inclines. So we're going to put everything that we've talked about all together. So here, I like to make sure that we still solve everything in terms of equations. So our equations would be, I have mass 1 times gravity on my first object. I have my normal force, which is perpendicular to my surface. And I have tension also acting on my object. Over here, I have mass 2 times gravity, and I also have tension. Now remember that I can already tell that these tensions will be the same, and if this object is accelerating, it will accelerate in the same direction, and it will accelerate at the same magnitude. So now that we've drawn our free body diagram, we're going to make sure that we break up our mass times gravity into its components. So this m1g over here, I'm going to break up into its components. Again, the angle given, that 30 degrees, is this one inside. So right next to it becomes m1g cosine of theta. And below it, I'm going to rewrite this mass 1 over here so that it doesn't get too confusing. And this bottom part becomes m1g sine theta. Now that we've broken it up into components, now we have to remember that we're dealing with pulley systems. So I can guess that my object's going to accelerate in whichever direction. So I'm going to say, hey, let's say that it's going to be accelerating in this direction. We'll call this positive. If you had called the other direction positive, that's okay. You would have gotten a very similar situation, but I want to show a result if we say that this direction is positive. So the sum of the forces, and here we can say that the sum of the forces in the x direction would be, for one object, m1g sine theta, minus tension, again that tension is going opposite the direction that we're saying, is positive, and that's equal to mass 1 times acceleration. And then for the other object, I'll say that tension is going to be positive because it's in the direction, and m2g is in the negative. And this is m2a. Again, 2 equations, 2 unknowns. We're substituting in for tension. So if I rewrite my first equation, I get m1g sine theta minus mass 1 times acceleration, is equal to tension. So I moved tension to the other side, and I moved m1a to this side. Now I have an equation for tension. Now I can substitute that in to my second equation. Now all we need to do is solve for acceleration. Move m1a to the other side, factor out an acceleration, and then the last piece to just divide by mass 1 plus mass 2. Again, you can see that we're getting almost the same relationship every time that we deal with a pulley system. And then divide by mass 1 plus mass 2. Now we have a value for acceleration, or we have an equation for acceleration. Because I already have all my numbers, at this point I can plug that in. When you put all your numbers in, you're actually going to see that your values are negative, or you'll have a negative acceleration. What that means is that your objects are not actually going to accelerate in this direction. They're actually going to be accelerating in the opposite direction. But this is true. This equation is true every time that you designate the left to be positive. So what that means is that if these masses were true, then my object would actually be accelerating in the opposite direction. Negative to the direction you said was positive. Now, once you get a value for acceleration, all you need to do is go back and plug in to either one of these equations to solve for a value of tension.